All right, so we have this question that we want to work on. So we'll try this question and see. Give me a moment. So this is a question on reflection seismology, right? So this is a question that we have. So given the seismic reflection data in the table below, determine the depth of the first intercept. Now remember that for reflection seismology, we have a graph. We have a graph as this. Then we plot t squared against what? X squared. Then we plot what? Our graph, right? And so the thing that we need for this graph is that we need to redraw our table. So we need to get a new set of table. Oh, why is my this thing like this? Come in. So we need to redraw the table. So the table that we have here. Then put to account our t squared and what our x squared, right? So we have x, then we have t. So we need x squared, then we also need what? T squared, because those are the values that we need to plot what? Our graph. So t squared. So the value that we gotten from the experiment was 2.5, 5.0, 7.5, 10.0, 12.5, and what? 15.0. And our t values corresponding to our 7.3, 12.6, 18.3, 24.1, 30, 30.0, and 36.3. So we just take the 2.5, we square it, right? So that's basically what. So 2.5 squared will give us 6.25. 5 squared is what? 25. 7.5 squared is what? 56.25. 10 squared is what? 100. 12.5 squared is what? 156.25. And 15 squared is what? 225. When we come to the t, we take t squared, 7.3 squared, that is 53.29. We take 12.6 squared, that is 158.76. Then we continue. This will be 334.89. And this will be 5. That is 24.1 squared is what? 580.81. Then 30 squared is for 900. Then 36.3 squared is for 1317.69. So this is the data that we need to plot our graph. You get it? So now we can come to the graph. So remember, these are the values that we need. So let me bring these values here to our graph. So let me bring my graph to the top so that we can work on it. So this is our graph. We need to plot the value that we had on the graph. So let me bring the values that we have here. Let me bring it to this side so that we can clearly see it. It's not working. No, I'm coming. So yeah, this is our value. So I'm going to bring it to the top so that we can work with it, right? Let me bring it down here. So this is our graph that we'll be plotting. Now if you look at the value string, so on the x-axis of the graph, we would have what? Our t squared on this axis, right? Then we'll have, let me zoom it down a little bit so that we can have a full page for it. Okay. Then on our x-axis, we have what? Our x was squared, right? Now let me let me bring the values that we are plotting here. So x squared, t squared. So the x squared, we have 6.25, we have 25, we have 56.25, we have 100, we also have 156.25, we have 225. Then the t values are 53.29, we have 158.76, we also have 334.89, then we have 580.581, then we have 900, then we also have 137.163. So we are going to plot this, right? Let me increase a little bit. So we want to plot these values, right? So the highest on our t-axis is 1300. So we can go by, let's say, if you start from, let me count them. We have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So we can go 10, 10, right? Will it be possible? No. So let's do it 2020. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2020 will go, so 10, 10 will do. So we can say so 20, we can go for 50, 50, right? So we can say 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, 550, 600, 650, 700, 750, 800, 850, 900, 950, 1,000, 1,050, 1,100. That one will not work. Let's take it as this is what we have, right? This is what we have. Yes. Let's take it that way. Then our x, we can go by what? 10, 10. So we can say 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180. 112 did not reach you. Okay, we'll manage it like that. It means that we are taking these last values out, right? These last values out so that we can actually plot it. Now, mostly we use Excel to plot, but I just want to give you a better understanding on how to go about this kind of calculation, right? So we take the 6.25, let's see somewhere here. Then we have 53, so around here we plot. Then the next one is 25, somewhere here. Then the 25 corresponds to 158, so around here. We are not plotting with accuracy, just that we want to give a very simple way. Then we have 56, so around here. 56 going to what? 334, 334, so 334 close to somewhere here. Then 100 going forward, 580, 100 going for 580, so 580 around here. Then 156, so 156 somewhere here, going for 900. Yes, 900. Now we have this. So what we do is that we draw a straight line through our point. We draw a straight line through our point. Now there is an intercept here. Now after getting this, what do? We are being asked in the question to find the velocity of the layer and the thickness. So finding velocity, I'll take my large triangle. So I'll see, let me use a different color so that I can clearly see. So I'll take my large triangle, the point there, and I'll use it to find my what? My gradient. So this will be my change in x, this will be my change in what? Y or t. So this is what we are doing here, is changing x squared and changing what? T squared, right? Okay, so with that in place, we can now proceed to our calculation. So if I want to find the gradient, so the gradient is equal to change in what? T squared over change in what? X squared. So with the point that I took, my coordinates, so let's call this point 1 and let's call this point 2, right? So point 1, the coordinates there are 6.25, 53.29. Then point 2, the coordinates there are 156.25 and what? 900, right? So we want to find the gradient. So the gradient in terms of the t, I will go for 900 minus what? 53.29 divided by what? 156.25 minus what? 6.25, and that will give us the gradient. So 900 minus 53.29 divided by 156.25 minus 6.25, and so I'm going to get my gradient to be 5.6447, and it is in milliseconds squared per meter squared. Now remember, in the question, the unit of time is in milliseconds. That's why this is our gradient. Now remember this equation. T squared is equal to x squared over v squared plus 4a squared over what? V squared, right? And we said that we can get our gradient out of this. So our gradient is equal to 1 over v was squared, right? So if I want v squared is equal to 1 over what? M. Are you okay? So I'm looking for v squared. So v squared will be equal to 1 over 5.6447 millisecond, right? That will be 10 to the power negative 3, but it is all squared, right? And so my v squared is going to be what? It will come up, it's going to be 10 to the power 6 over what? 5.6447. And this is in this is in meter squared per second squared. So that's the unit now. So 10 to the power 6 over 5.6447. So my v squared, so when I move down a little bit, so I can see that my v squared is equal to 177157.3334 meters squared per second squared. But am I looking for v squared? No, I'm looking for v. So v is equal to square root of this answer. So 177157.3334, and that will give me what? So square root of the answer, that's equal to what? 420.9006 meters per second. Now after getting the velocity, the next question asks us to find the what? The height. Now see the height. Now the height can be gotten from the intercept. So if you look at this equation, we can liken the equation for reference. So you know that this equation t squared is equal to s squared over b squared plus 4a squared over what? B squared. And we compare this equation to y is equal to mx plus what? C. So our intercept is equal to this whole thing, right? So we go to the graph and go and read our intercept. Go to the graph and read our intercept. So our intercept will hover around, where's my listing? Our intercept will hover around this place, so we can take it. You see, this graph has not been drawn to scale. Mostly with these huge kind of values, we mostly use Excel to plot the graph. So let's assume that when we check from the graph, or maybe they give us a convenient values, when we check on the graph, our C was what? 11.91, right? And the unit for it is what? Millisecond squared, right? So if this is our y-intercept, then that y-intercept, that's C, is equal to what? 4h squared over what? V squared, right? And we are looking for what? H. So making H the same, I'm going to get C V squared over 4 is equal to what? H squared. I'm looking for H, so my H will be equal to square root of what? C V squared over what? 4. And you know what C is? The y-intercept, right? So finding H is going to be square root of C, which we had 11.91 times our vein that we got, that is 420.9006 squared, right? All over what? 4. So we just put this in the equation. So 11.91 by 420.9006 squared all over what? 4. And that will give us what? The height. That will give us the height to be equal to 726.2 meters. In kilometers, is going to be what? 0.73 kilometers. And that's the thickness of the wave. So this is just to introduce you to some basic questions under this. Now our main focus for the day is what? Let's move to it. So we are going to look at the variation. We're going to look at the variation. Very important. So the causes of variation of the force of gravity, and that's what we are going to look at. But before that, let's look at the Earth gravity field. So we're going to look at the Earth gravity field. The Earth gravity field. Now we all know the Earth gravity field. Now, first of all, we need to know what gravity is. Gravity, we know, is a force of attraction on a body exerted by the Earth towards itself. So what it does is that, assuming this is the Earth and there is a body on the surface of the Earth, let's say this is the center of the Earth, there's a force that is drawing this body towards the center of the Earth. So the Earth pulls things towards itself, and that pull of things towards that kind of attraction is what we call gravity or gravitational force. Now, if I'm on the Earth's surface and I release a body, the body will begin to fall, right? Now, as the body is falling, it will fall with a certain velocity. Now, as it falls, the velocity will increase as the body falls. And this velocity that will increase is as a result of what? Now, this velocity that will increase, the increase of velocity will be constant, or it will happen at a constant rate. The velocity will not be the same, but as the body is falling, the velocity will increase. But the increase that will happen will be at a constant rate, and that constant rate is what we call acceleration. Now, this acceleration is due to the gravitational force of attraction. You get it? So that is what where we had, or the place that we got acceleration due to gravity from. Because gravity or the earth is pulling object towards itself. When we leave an object close to the surface of the earth will pull it towards itself. And as the earth is pulling it towards itself, the body will fall at a certain velocity. And as the body is falling, the velocity of this body will increase. And the increase will be at a constant rate. And that is what we call the acceleration. We are seeing that this acceleration is due to what? Gravity. Now, Newton's law of gravity, or Newton's gravitational law, it states that the force that exists between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So putting these two together, we are going to have F is directly proportional to M1, M2 over what? R squared. Now removing the proportionality sign, we have G, M1, M2 over what? R squared. Now just as we explained, M1 and M2 are the masses of the body, and R squared is the distance between their centers. Now G is the universal gravitational constant, universal gravitational constant. And in terms of magnitude, it is what? 6.673 by 10 to the power negative 8 centimeters cube per gm second squared, per gm second squared. Or we can see that G is equal to 6.673 by 10 to the power negative 11 meter cube per kilogram second squared. So that is the universal gravitational constant. Now, because we are dealing with the earth, the force of gravity that is associated with the earth and the body is given by G m. That is the mass of the earth and the mass of the body over R e, the radius of the world, the earth. So now we are seeing that there is what we call variation of the forces of gravity. For instance, if I go and stand on Mount Everest and I measure the gravitational force that is acting on the body there, and I come to a place, maybe a lowland, and I measure the force of gravity there, you realize that there are differences. You get it? So let's take our campus for instance. If I measure the force of gravity at, let's say, N block, and I go to, let's say, Kumapli to measure the force of gravity, there's going to be what? Differences. And so we want to know what accounts for these differences, and that will lead us to what we are calling the causes of variation of force of gravity. So causes of variation of force of gravity. So I said that the force of gravity is not the same everywhere for the same object due to some physical variation of the earth as a body. So just as I indicated, the force of gravity is not the same everywhere for the same object. So if I take the same object, for example, even this, let's say this, the surface of the earth, and I take an object here, I measure the force of gravity that is acting on the object, and I take that same object here, measure the force of gravity that is acting on the object. So this is F1, this is F2. They are not the same, and this is due to the physical variation of the earth body. So what are these physical variation? Let me use this to write it. So the first one is the oblate nature of the earth. The oblate nature of the earth. That is the first. Then 2 is centrifugal force as a result of the rotation of the earth. The next is what we call excess mass. Excess mass. The next one is the changes in density. Changes in density of rocks within the earth crust. Then the last one is what? It's what we call topography of the earth surface. The fifth one, topography of the earth surface. So I'm going to take each one of them and what? I will explain it. I'm going to take each one of them and explain how does the oblate nature cause variation and so on and so forth. So we are going to explain each one of them so that we can have a better understanding of the work that we are doing. All right. So let's see. So first of all, we are going to look at the oblate nature of the earth. The oblate nature of the earth. Oblate nature of the earth. So if we take the earth, we know that the earth is not a perfect sphere. It's not a perfect sphere. So let me assume this is the earth. I'm not drawing it well. Let me draw it. Well. So let's assume this is our earth, right? Now let's say this is the equator. Is that the perfect place to put the equator? Let me put it here. So let's say this is the equator, right? Now this is the center of the earth. Now this is also the poles of the earth. So the poles of the earth is the equator. Now from the distance from the distance from the center to the equator, at the equator, the distance from the center to this end to the surface of the earth will be the radius of the equator. Then the distance from the center to the poles of the earth will be the radius of the pole. Now if you look at this very carefully, the radius at the equator is greater than the radius at the pole. Now you remember, force of gravity depends on what? The radius that is between the two bodies. So if a body is at the equator, let's say this, let me give it a different color. There is a body at the equator. The distance from that body to the center, where it's known as the concentration of the earth mass is RE. Then if the same body is placed here at the pole, the distance from the center of the earth to the pole or to the body is RP. Now, if you look at this carefully, the force of attraction that will exist between the body and the earth, in this case, I'll call it FE, will be lesser than that is being exerted on the body at the pole. This is because if RE is greater than RP, then the force of attraction at the pole, which is given by JM M1 over RP squared, FE, which is also given by JM M1 over what? RE squared. Now, all the other parameters are constant, but their radius changes. Now, because RE is big, gravitational force of attraction will be small, and because RP is small, gravitational force of attraction will be what? Big. So in this case, the force of gravity at the pole is greater than the force of gravity at the equator. Now, when I move from the equator towards the pole, I am changing what we call latitude. So when I move from the equator towards the pole, my latitude keeps on changing. And so my radius of latitude from the equator to the pole decreases. So because the radius of latitude from the equator to the pole is decreasing, right? Then if I also move from the equator to the pole, gravitational force of attraction will increase. As simple as that. So it as it's here, it's considered as the least, but as it moves from the equator towards the pole, then it is what? Increasing. Do you get it? So it is what? Increasing. So as simple as that, right? So points at the pole are closer to the center of the earth and therefore experience a greater force than the points at the equator. So this is the first variation that is caused by the oblate nature of the earth. Then we'll go to the second variation, that is the rotation of the earth producing centrifugal force. So the next one is the rotation of the earth producing rotation of the earth. Now, we know that the earth rotates on its own axis, so this is the earth. Let's see, this is the axis of the earth. Let me draw these latitudes. I'm not drawing this thing well. Let me erase and take a different color and draw this thing well, so that you could clearly see what I mean. So if this is the earth and this is the axis of rotation, imaginary, that passes through the earth. Let's say this is my latitude. Right, so I have another here in this direction, and in this direction, and this is my equator, right? This is the center of my equator. Now the earth rotates, right, on its own axis. So if there is a body here, let's say a body here, and the earth is rotating, initially there will be force of gravity between this body and the earth, right? Force of gravity, let me call it Fg. Now, as the earth is rotating, the centrifugal force will be generated that will try to throw the object away from the Earth's surface. So this is a centrifugal force. So it tries to throw the body on the Earth's surface. It tries to throw it away, right? Now, what is centrifugal force? It's given by the mass of the body, then the angular velocity of the what? Of the body square, then the what? The radius of latitude. Now, the radius of latitude is the distance from the axis of rotation to the point where the object is. So this is the radius of latitude, right? Okay. Now, as the body moves, let's assume that it is here. If the body was here, then the radius of latitude is the same as the radius of the equator. Now, as the body moves away and gets towards the pole, let's say the body gets to the pole. At the pole, that is where the axis of rotation is. So at the pole, the radius of latitude is 0. Now, centrifugal force, which is given by this expression, yeah, 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 yeah. So if you look at the equation, the mass of the object doesn't change. The angular velocity of the Earth doesn't change. So what changes is what? The radius. So as you move from the equator towards the pole, the radius of latitude will decrease. So from year to year, radius of latitude will decrease. And so the centrifugal force decreases from the equator towards the poles. So when this happens like that, we know that centrifugal force is in the opposite direction to the gravitational force. So as we move from the equator towards the pole, the centrifugal force is in effect is going to reduce the gravitational force at a given point. But when it gets to the poles, because there is no component of centrifugal force, we are not going to have any effect. Are you okay? Okay. All right, so that is how it's going to be. So the centrifugal force will increase at the equator, decrease at the pole, and when it increases at the equator, because it's in the opposite direction, it's going to cause the gravitational force to reduce, because when it is resolved. So what you can say is that if the object is at the pole, the centrifugal force is 0. And if the object is at the equator, then the force is greatest. Since the radius of latitude is greatest at the equator, now since the centrifugal force is in the direction opposed to the force of gravity, the resultant force of gravity at the poles will be the greatest, all things being what? Equal. So that is it for the rotation of the Earth. So the rotation of the Earth results in centrifugal force, which tends to what? Reduce the gravitational force. Now, as you move towards the pole, this centrifugal force diminishes, and so doesn't have any effect on the gravitational force. Do you get it? Now we take the next variation problem, which is excess mass. So the next variation problem is what we call the excess mass. Now, the Earth, this is the Earth. We have, oh, not drawing these things well. So if this is the Earth, let me change the color. Now, this is what we call the excess mass. Now, the explanation for the excess mass is a little bit tricky, so you have to pay attention. Now, this is the center. Now, if there is an object, let's see, let me call this object here, and there's an object here. Now, if you look at the equator, there is excess mass, excuse me, at the equator. So, a greater mass of the Earth is at the equator, at this side. Then as you move towards the pole, the greater mass of the Earth diminishes, right? Now we know that gravitational force depends on the mass of the Earth, right? So assuming this excess mass that will add up to the original mass of the Earth is, let's say, me. So now my mass of the Earth now becomes m plus what? Me, right? Then at the pole, because this excess mass is not, see that at the pole, the mass of the Earth is still m. So in that case, the gravity equator is going to be given by m prime, the radius of the equator squared. That of the pole is going to be j m m1 over what? Rp squared. Now, because of the excess mass, keep in mind, because of excess mass, or in the context of excess mass, gravitational force at the equator is greater than the gravitational force at the pole in the context of what? Excess mass. So if we are explaining it in terms of excess mass, because of the greater mass at the pole here, sorry, at the equator, is going to add up to the original mass of the Earth. And if that mass is increased, gravitational force is going to increase. So if that mass is concentrated at the equator at this side more than the pole, then it means that the gravitational force that would occur at the equator is far greater than what? At the pole, in the context of what? Excess mass. Do you get it? So that one too have been dealt with. Then the next one is the change in density of rock. So that one is very simple. So change in density of rocks. Change in density of rocks. So when we talk about change in density of rock, we know that the crust is made up of different rock types, right? Different rock types. And these different rock types, when you move vertically down the earth crust, it changes, and when you move laterally, the rock types also changes, and each and every rock has its own composition and the properties that it will exhibit. So if I measure the gravitational force within a terrain that is underlaid by shales, the gravitational force that I'm going to measure, if I take that same body to a different place which is underlain by granite, the gravitational, although the body is the same, the gravitational force will differ because of what? The different rock types that were within the terrain that we did our measurement. So it also plays a role. So they say changes in the density of rocks within the earth crust due to its heterogeneity causes minute variation of gravity force. As simple as that. Then, if we want to know mathematically how this occurs, let's see. We know that the gravitational force of a body is given by m1, that is the m of the earth, m1 of the body over what? R squared. And we also know that force is equal to the mass times acceleration due to gravity. So I can equate this equation. So I can say that m1 over R squared is equal to what? m1g. Now m1 will cancel m1. So I can see that, oh, I forgot to bring the gravitational constant. So I can say that G is equal to G M over what? R1 squared. Now we know that mass over volume is what? Density, right? And so density will be equal to what? Mass. And so mass will be equal to what? Volume times what? Density. Now the volume of the earth is given by 4 on 3 pi r cube. And so the mass of the earth is given by 4 on 3 pi r cube multiplying the density of the earth. Now I can replace this into this equation. So I can see that G is equal to capital G multiplying 4 on 3 pi r cube rule divided by r1 squared. So this will cancel two of this. So here will be left with r. So G is equal to G 4 on 3 pi what? R rule, right? And so G is equal to 4 on 3 G pi r rule. And so the acceleration due to gravity depends on what? The density of the material, within the terrain. So very, very what? Important. And this density can influence the acceleration due to gravity. Are you okay? Then the last one that we'll look at is topography. So the variation can also be due to topography. I want to look at it. So the variation due to topography. Now we have 3 instances. If I measure, so assuming this is the surface of the earth and this is, let's say, a mountain. The mountain is at a certain elevation, let's say H. Then from the center of the earth to our reference point is R, right? Then there is a body here. Now, topography will also have an effect on the gravitational force. It either increases it or decreases depending on the topography. So in this case, let's see what will happen. Now, our force due to gravity will be given by G M of the body over R plus H squared, because now the distance is from here, from the center to the body. And now because the radius or the distance between them has increased by a factor of 8, it means that the force of gravity is going to reduce. So this is the first case. So when the force of gravity is measured at a certain elevation of the earth, it's going to reduce gravitational force. Now, what if we measure or we do the measurements close to a mountain? So not on top of a mountain, but close to a mountain. So assuming here, so we do the measurement close to a mountain. This is on top of a mountain. Now we said that on top of a mountain, it's going to reduce gravitational force. Now, if it is close to a mountain, what will it do to it? If it's close to a mountain, what will it do to it? Now, there is a mass concentrated in the mountain that will sort of attract the body. So it will attract the body to itself. Then the earth is also attracting the body downwards, right? Now let's call this force F1 and let's call this force Fg, right? Now because there is going to be attraction, if this force is resolved, if it is, let's say this is an angle here, if this force is resolved, it's going to be in the opposite direction, right? So as gravitational force is pulling the object towards itself, this force, as a result of the mass within the mountain, is also pulling it away, and so it's going to also what? So reduce gravitational force. It's going to reduce gravitational force. Are you okay? Then the last one, if the measurement is done close to a valley. So the measurement is done close to a valley. Now here, in this case, we consider the valley to be what? To have a mass deficiency. A mass deficiency, because there used to be materials here and now there is no material. So the mass of the earth has now in this case reduced. So let's say, assuming the mass of the earth was initially m, because of the mass deficiency, a certain mass, let's say the mass that is taken out that created the valley, is now going to be subtracted from it, and so it's going to create a new mass that is very small compared to the initial mass. And so we also know that gravitational force depends on the mass of the earth, and so in that case, because the mass has decreased, gravitational force will also reduce. So in the aspect of topography only topography reduce gravitational force. All right, so this will be the end of this section. What we'll do is that we'll add the bougie one to it, and that will be all. Thank you very much for watching.